first thank Professor Danino for inviting me to be part of this series. It's quite an honor, and especially now that I find out with what thought the entire course has been put together. And the other thing is, it's not every day one gets introduced by a Padma Shri, and so it is quite a privilege. And especially since there are very few Padma Shris in the academics, and very few of them who are richly deserving as Professor Danino. So it's a real privilege for me to be here and present my work today. Okay. What I'll be talking about is the Uncool Dam, which is a stone dam. The location is about 10 or 11 kilometers south of Delhi. Okay. And effectively, the research was carried out by excuse me, 3 students: Sandeep Garg, who was a B.Tech student; Vijay Srinivasan, who did his master's; and a small part was done by Ramesh Babu as part of his M.Tech thesis. And the colleagues who were involved with this, one is Professor J.P.S. Oberoi from the Delhi School of Economics, and Professor Kale from Mechanical Engineering at IIT Delhi. This project was funded entirely by whatever resources we had at IIT Delhi. Okay, so there's no project that we got funding from. Okay, now I joined the Applied Mechanics department in 1991, December, so effectively 92. And we started this particular research in 93 or 94. So I feel I should give some explanation why I started quite a different line of work from my original training. So the conventional engineering that I do, part of it is in the fundamental area. It's one of the problems we've looked at is hydrodynamic stability theory applied to wall turbulent flows, which is very esoteric. And then we're looking at now the interaction of free stream turbulence with a turbulent boundary layer. The application would be something like atmospheric turbulence interfering with the boundary layer on an aircraft wing. Okay, and in the applied on the applied side, we're doing some work on vertical axis wind turbines. I've not put any names there because the collaborators are quite a few. And then I'm looking at some problems of solid fluid interaction. And one very practical problem is how to look at the ventilation inside non-AC buses and trains. Again, that is with Professor Kale. Okay. Now, on the engineering alternative side, we've looked at a few examples of traditional engineering. One of which, the first one is what I'm going to talk about in some detail today, and the second one I will discuss tomorrow. I think you had a brief from one of the students on the second problem. And if time permits, today I might spend a few minutes on the last one, which is the traditional water harvesting systems of Rajasthan. Okay, now, if you'll permit me, I will give a sort of longish introduction on why we got into looking at these traditional engineering structures and why we got into this entire line of research. When I joined IIT Delhi, that was the time when the agitation against the Sardar Sarovar project or the Narmada Dam was at its peak. And I think every other day you would hear news of Medha Patkars, hunger strikes, and agitations by the local people who are affected by the dam. So this was going on in the news, and there are several questions that arose. The first is this just someone making a fuss so that they get their name in the paper? Or is there something really, is there some truth to this agitation? And are the problems really significant? And very easily one could see that, yes, there are significant problems created by this. Such a large dam. And I think at that time, right now the dam height is 160 meters. At that time it was less than 80 meters. Even then, several of the problems were evident. Some of the what we call side effects of large engineering projects. One, of course, when you build a dam, the reservoir submerges a large tract of land, pristine forest land, And along with that, you have displacement of people. And the people, maybe in some ways you can rehabilitate elsewhere if you plan properly, but there's a considerable destruction of flora and fauna, which you don't, you can't do anything about. Then downstream of the dam, the river flows are reduced, right? And therefore, whatever cleaning activity or fishing activities that would happen downstream of the dam is affected by this. And one very important problem is at the mouth of the river, you would get saline water from the sea ingressing well inland, and that is very serious because the mouth of the river is usually the most fertile region where a lot of agricultural activity is done, and that is that becomes not feasible once the dam is built. In this case, the first 2 points would affect large parts of Madhya Pradesh, but the salinity ingress would affect Gujarat also. Okay. Then, of course, once the reservoir is full, there are several other problems that are associated with it. One of the least, I guess, or depending on how you look at it, is the incidence of mosquitoes around that area. But the more serious one is the waterlogging of the land around the reservoir. And the usual way these large projects are handled is that there is a cost-benefit analysis done, and somehow you try to show that the benefits outweigh the costs. But even if you can do that, and even if you have done a fairly thorough job of accounting for the benefits and the costs, the typical dam life in India, a project of this type, the typical life in India is about 100 years. Okay? And after 100 years, the dam stops functioning, but the environmental damage that it's left behind might last for a few thousand years. So if you look at it that way, I don't know whether you can justify it at all. Now, one thing you should realize that the whole engineering of large dams was sort of perfected in the US and in Australia. And there, the silt load in their rivers is so low that their reservoir life is usually of the order of 1,000 or 2,000 years. So there may be the benefits and the destruction is of the same order time scale. Yeah.
So what do you mean by life of a dam? So what exactly happens after 100 years?
Okay, yeah, I should clarify that. The Indian rivers bring a lot of silt load because they flow through mountains which are not very rocky. The Himalayas are sedimentary mountains, so they break up and flow with the water very easily, and therefore over time the reservoir gets fully silted up, and then effectively the water carrying capacity of the reservoir diminishes over time, and the typical life estimated is about 150 to 200 years, but in actual practice, once the siltation starts, it is very progressive, and you might not go beyond 100 years. Okay. So sorry. I'll see if I can get back to my mouse. Okay, so the problems are, as I said, are very real. Now, the second question is it really a problem of engineering? The engineer's job is just to build a dam and let the sociologists worry about the displacement of people and the zoologists worry about the flow. Hello? The problem is if you are a good engineer, then you have to take care of the problems that you create. So we cannot really escape from the responsibility by saying that we just take care of the dam and let someone else worry about the problems caused by the dam. And the last question is this just something peculiar to the Narmada Dam, where the designers or the engineers here incompetent, or is it something more systemic and something deeper than that? And again, it's not very difficult to see that any such large project would necessarily have tremendous environmental impacts. So it's not a question of bad implementation or incompetent group of engineers, but it is a problem of bad design or bad engineering and bad science. The other reason for our getting into this is that what I found was most of the discussion of these problems happened outside the university and outside IIT Delhi. It was mainly in the newspapers. There were discussions between non-governmental organizations, but it appeared that this problem had bypassed engineering institutions completely. I found out later that there probably is a good reason for it, because most of the, or some of the people at least, involved in the decision making do come from IITs, and probably one of our deputy directors at the time of when I joined was party to some of the decisions. So there is a good reason why IIT Delhi was not involved in the critique. Now, the other thing is that, is this just a problem of the large dam? Or are there side effects for other engineering projects also? And I think this is a topic that people are fully aware now. Almost any scientific advance or technological advance brings with it a host of problems. And I've listed a few here. You can see deforestation, air and water pollution. Those of you, some of you may have noticed that being exposed to the really polluted air in Delhi, I'm condemned to wear a nose filter almost the entire day. I cannot get by without it. But that is what we have done to our air and water. Then the other things, global warming, climate change, everyone knows. I just want to briefly point out a quote by a Native American chief. And this is what he wrote in a letter to the President of United States. I don't know whether some of you may have seen it. I don't know if you're aware. It's called Chief Seattle's letter. Okay, and this. Oh, I don't see it here. Okay, it's not. It's showing on my screen, but not here. The statement. One of the statements he makes there, when he's discussing how the Native American reacts to the American development, is that he says that continue to contaminate your bed and you'll one night suffocate in your own waste. And every morning when I look at the air quality index in Delhi, I'm haunted by that remark. And guess how long ago he said this? It was said in 1855, about 150 years ago, when he saw the situation in American cities. And I mean, it's not a very long letter, but a really powerful critique of modern development. Okay, so now, but if you look at how science and engineering is taught in your textbook, everything is very systematic and logical, right? You have very strong foundational principles, and you have a very rational method of analysis and rational method of arriving at a final solution. Then where is the problem? So if after a series of logically impeccable arguments and steps, one still arrives at a solution which is inherently destructive, then where does the problem lie? It can only be in our starting assumptions. And therefore, we need to question the starting point of science and engineering, and then see whether there's another method of carrying out the entire enterprise. Now, one of the first things you're told in science is that science and engineering has to do with facts. Value is not part of the budget in any equation. In any of your analysis, value is separate. value, if at all, comes from the scientist or the engineer. It is not part of the foundations of science itself. It is only dealing with facts, verifiable facts. So you can have a statement like Edward Teller is a nasty human being, but he's a great physicist. I mean, he's the person who fathered the hydrogen bomb after Hiroshima and Nagasaki, right? And the other dichotomy is that science, the study of science and ethics is completely separate. So what it means is that we can address questions like, can something be done? That is a valid scientific question. But ought it or should it be done is outside the purview of science. This is not my analysis. I was fortunate enough to be in discussions with a couple of philosophers, one from Karnataka University, Dharwad, and one from Delhi University, Professor K.J. Shah and Dr. Anuradha Shah. So this is their reading of the scientific enterprise that I'm borrowing. Okay. Another way to look at it is that, which is what Professor Roy pointed out to me, is that all our large projects start with a clean slate. What that means is that they assume that there is no purpose or order to nature other than what is imposed by us. So the river flowing to the sea is of no use. It's just going waste to the sea. It has no additional purpose until we dam the river and then use the water for irrigation or drinking or whatever. The river by itself has no original purpose. So just to reiterate the point, in this enterprise, then, well-posed problems are of this kind. If you ask an engineer to design a car that can accelerate from 0 to 60 kilometers per hour in 5 seconds, it can be done. If you ask someone to, I mean, it might be difficult, but you can send a manned spacecraft to Mars. But if you ask a second type of question, how many automobiles can the environment around Gandhinagar support, provided over a period of something like 1,000 years, then we have no way of even thinking of how to start addressing that question. Or how many wind turbines can be placed on the coast before the climate is adversely affected. And the reason is for that is most of our powerful tools are what are called reductionist. We can take a complex problem, break it into simple parts, and apply very strong analysis on it. For example, the starting point in any discussion of mechanics is the free body diagram. And it's a very powerful thing. We want to analyze a small part of the system. And somehow, the hope is that once we have broken up a large system into simple parts and optimized things, when we put it back together, it will magically fit. And that is not always the case. And if it doesn't fit, we have no way of understanding how to fix it. When you look at something like the free body diagram, people sometimes say that you can see what the small part is doing to the rest of the system by using Newton's third law. That is, action is equal to reaction. So if you know the action, you can get the reaction. But the problem is in an open system, you don't know what either of them is. And if you really want to look at something like 1,000 cars and the atmosphere of Delhi, then you can't look at the car. You have to look at the entire atmosphere before you can address that problem. And very few books on mechanics are honest about this. I think probably the only one I found is a small book by Maxwell, where he clearly says that we can only address problems of the system that we have isolated. We cannot see what the system does to the rest of the environment. And if we need to do that, the environment has to be included in the system. Okay. The other thing is, say in thermodynamics, the starting point is an isolated system, again, which is an abstract construct, which has absolutely no bearing with anything that we do, because everything that we're dealing with in life is an open system. So then the question was, is there another way of doing this? I'm sorry, it's a very long introduction, and that is, and the hope was by studying examples of traditional engineering, we would get to this. Okay. Now, our interest in traditional structures, therefore, did not come from primarily from an interest in history or looking at examples to sort of highlight our glorious past. The idea was to see whether there is something in them that allows us to do our engineering differently. There is, some evidence, and everything that we studied only seems to strengthen that in saying that most of our traditional engineering systems which have survived seem to function in a way that sustainability is intrinsic to their method, and which means that can we do something, ought we do something, seems to have been answered together when they were designed and put together. It's not necessarily that all small systems are good. So some people argue that large systems are inherently bad and small systems are good. To an extent, yes, but you can do a lot of damage with very small systems if they are replicated en masse. For example, in a large irrigation project, a tube well or a bore well is a very small thing. But if you indiscriminately put thousands of tube wells, then you can destroy the groundwater. Okay? So it's not a question of big and small. Now, there is another, there's some other evidence, not just from the structures, but from the texts that are written about these. And I'll just give you one quotation from a text on architecture called the Maya Mata. Okay. It, among various other things, it has a section on when you're constructing a building or a temple. The passage preceding this is what are the trees that are useful. So it lists a whole number of trees like teak and sisam, etc., which can be used for construction. And then after that, it has a section on this paragraph on the trees to be avoided. So the chosen tree should not be close to a temple, should not have been struck by lightning, nor scorched by any conflagration. It should not be growing in a place inhabited by spirits, nor beside a major roadway, nor in a village. And there are several more sentences. They should not be frequented by birds, nor by wild animals. They should not be dead, nor serving as shelter for Chandala, nor for any men of any caste whatsoever. And then some more. They should not belong to any god, deity, nor should they be found near a tank, well, pond, or like place. Caveats placed before you can actually cut a tree that you will use for your building or your temple. Okay. Now, what does one make of it? One reaction would be to say that this is all bunkum. Obviously, this can't be serious because you can't find such a tree, right? But look at what is being done. You're being constantly reminded that even if you don't see the purpose, the tree is serving some purpose. So it might be, and the purpose may be physical, it may be metaphysical. So it could be serving some spirits, or it could be serving some animals. There are also recommendations based on the strength. If it's struck by lightning, obviously the wood will be weakened, and therefore for an engineering purpose, it's not useful. So it's, the entire thing is all mixed up. There are issues of strength, of what is good quality for construction. At the same time, there the requirements of not just human beings, but non-human nature, and maybe not even material nature, which has to be taken into account. So the reminder is constantly that when you undertake a project, you have to be very, very sure that it's absolutely necessary, because you are doing a lot of damage willy-nilly to the environment. Yeah. It is a textbook on traditional Indian architecture. It's a book written, I think, I don't know whether it originally Sanskrit or Tamil, but it's been translated into English. So we have access to that. Again, by a compatriot of Professor Benino, Professor Bruno Dagen is the one who translated it. Okay. So that is, so the approach then would be to look at these traditional texts and try and get the method. Unfortunately, not many of them are available in a language we can understand. And even if they are translated, the style and the way the material is presented is very different from an engineering textbook of today. It would somewhat, it is very prescriptive. In a way, it is similar to our design codes, which are meant for an average person to follow so they don't make mistakes, rather than for someone to understand the theory. Okay. So the better way we felt was to actually look at an engineering structure. I'm sorry, now I'm finally coming to the main topic, okay, which is the Uncool Dam. We were very fortunate that Professor Oberoi had been looking at this dam before we got into discussion, and as a sociologist, he had discovered that this was fairly well preserved and not very far from Delhi, and so it was a very nice example for us to look at. So the dam itself, the overall length is about 100 meters, the height is about 12 meters, and the width at the top, I will show you detailed pictures, about 20 meters, and at the bottom, obviously, it flares a bit, it's about 30 meters. By the international classification on dams, it does not fall under a large dam. Anything for a dam to be classified as a large dam, it has to be above 15 meters. Okay. The location, I've given the latitude, longitude, but really the easier way to locate it is that it's slightly south of Surajkund, which is a well-known landmark in Haryana, and it's about 10 kilometers south of Delhi. It's a stone gravity dam, okay. And there is some confusion about when it was built. It was either built by King Anangpal I or the second, which means the date could either be 7th century or 11th century, but definitely we know it's older than the 11th century and newer than the 7th century, so it's at least 1,000 years old. Okay. And again, this is a map that I've taken from an ASI report, and this part is, you can't see that. So Delhi is here, and Faridabad is here, and so Anandpur is somewhere there. A more detailed view, again taken from an ASI report, is shown here. So this is the Surajkund, which is a well-known sun temple, and it's in the news because every year a big festival is conducted near this Surajkund, where artisans are invited from all over the country and from abroad also. And it's usually in February, and we just finished the Mela on 17th February. Okay. Now, next to that there is a lake, and the dam is about 1 kilometer, little more than 1.5 kilometers south of Surajkund. Okay. And that's the orientation of the dam. Now, the Anandpur village is somewhere here, and if you go in this direction, you get to the foothills of the Aravalli hills. And in that direction, there is a drain going to the Yamuna. Okay? So this is the topography. The hills are here, and the land is sloping from left to sort of left and bottom to the top. Okay? Here is something I've downloaded from the internet. It's a pretty picture of the Surajkund, and I don't know whether you can, to get the scale, this is a person standing here. And this is a recent picture of the Anandpur Dam itself. Again, this is from Google Earth. So you can see again, this side where you see this sort of channel, narrowing channel. This side is towards the Aravalli Hills, and this side is towards Surajkund. Okay. Now, I don't want to say upstream and downstream because there is a little bit of problem, and but I would refer to this side as the Anandpur side and this side as the Surajkund side, or the Badarpur side. Again, this is a photo of the Anandpur side that I've taken from the internet. You can see the construction. It is this is 1,000 years old. We didn't notice any cracks when we went on our field trips in the mid-90s. Okay. and there was lots of overgrowth here, but if it's cleaned up, it is perfectly in good shape, and it can still function if the rest of the system is revived. Okay. Okay, that when we looked at the dam and looked at whatever reports were available on this, there were some things that puzzled us. One of which was that if I look at the topography, the Anandpur side is where the water must flow down from, and it must discharge towards the Suraj Kund side, which means if it is to be a dam, then the reservoir would be on the Anandpur side, and the region where there could be some benefit from the dam should occur towards the north or towards the Suraj Kund side. On the other hand, if we look at the topography in greater detail, the land is flat on the Anandpur side, and you have a deep gorge on the Suraj Kund side. Okay. Also, some features of the construction of the dam indicated that the flow was actually going from the Suraj Kund side to the Anandpur side in at least part of the dam. And some other features indicated that the flow was going from the Anandpur side to the Suraj Kund side. So there seemed to be a confusion about which way the flow is going through the dam and what the dam is meant to do. Okay. Then the other thing is the dam had sluices at 3 different levels. And one of the conjectures put forth in the ASI report is that the dam was constructed and then it silted up, so the height was raised, and another set of sluices were built. Again, it silted up and the height was raised a third time, and or a second time, and then the last set of sluices was built. But when we examined it, we didn't find any indication that it was constructed in 3 different phases. It looked like one coherent piece that was made right from the beginning with 3 different levels. The other peculiar thing is that the sluices are meant to control the flow through the dam, and if you want to block the flow, you just need to block the upstream end of the sluice. This particular dam had provision to control it from both ends, again, which is very unusual. You might think that it's a mad designer going in for symmetry where none is required, or there might be a slightly more important reason why this dual control is provided. The thing is, of course, when you have the dam, you don't want to trap water inside the dam. So the control would always be on the upstream side, where the water is to be held. Okay. The last thing that the ASI report said was that on the Suraj Kund side, there was a little pool of water, and again, from the topography, that is the downstream side. So the conjecture was that the foundation of the dam was leaking. Okay. In fact, when we did our first field trip, it was, I think, February or March, and there was water on the Suraj Kund side. Now, this is a drawing which gives some details. Let's look at the elevation first. There are 3 levels of sluices, as I said. This is the bottom 2, then there are 3 in the middle. This central one connects to this funnel that is shown on the Anandpur side. And then there are 2 at the top. These 2 connect to a channel here which runs down this slope, and then there is a little receptacle made at the base here. If I look at this structure, it would appear that the flow is going from top to bottom. But if I look at this structure, it appears that the flow is meant to go this way, run down this slope, and assemble there, and collect in this receptacle. So there is either the designer was very confused, or the operation of the dam is not so straightforward. Okay. Again, if you see these side abutments, they are on the Anandpur side. Now, if if this is the reservoir, you would expect the abutments to be here, not on this side. if the reservoir is on this side, that is when you would need to provide these these structures to hold the dam in place. Okay. Now, if you take a look at the cross section, then this is the Anandpur side, and the ground level is about 6 meters higher than on the Surajkund side. Okay. This is the reason why the ASI report felt that the dam had silted up, and it was built in 3 phases. Okay. But what we feel is that this is how it is meant to be. The bottom sluices are meant to operate underground, and actually they come underground and connect up to the receptacle into which the top sluice is empty also. So the points we noted fairly quickly is that, as I said before, there are no sign of 3 stages of construction. It was one coherent structure. The sluices from the top level, mid level, and bottom level sluices, they were all of approximately the same height. I think that we can see here. This is the height of the sluice which is going in the top. This is the height of the sluice going in the middle, and this is the height going at the bottom. All of them are about 1.8 meters, but the width changes as you go from top to bottom. The 1.8 meters means a human being can walk through the channel, and if you want to do any maintenance work, then this height is required. But the top level sluices would have to have a larger cross sectional area, because the hydrostatic pressure available for flow is less there, so they are a bit wider, and when you go to the bottom, they are narrower. So it has been very carefully done to allow very easy access to the sluices, but at the same time keeping in mind the requirements at the top and bottom. So the top one is 0.7, and it goes down to 0.45 at the bottom. As I said again, the sluice can be controlled at both ends. And the bottom sluice also has an interesting construction. It is built in this way. At the end of the sluice, where you need the gate to operate, it does not operate just in a channel, but there are 2 stones with holes in them, and so you have 2 slabs with holes in them, and then the gate operates between them. Now, there are 2 reasons for this. One is you can control the flow more easily, because you can control the size of these holes. The other one is, if there is any silt or sand in the vicinity of this channel, then these tabs would prevent that from interfering with the functioning of the sluice gate. So it is a clear indication that the bottom level sluices were meant to operate under soil. They are not, yes?
What would be the mechanism for lifting the gate?
That there would be the total height is about 12 meters. So you could have a rope and pull it from the top. Okay. So those, sorry, I don't know what happened there. Those things, they have not, the gates themselves are missing. Yeah. These are all stone, stone. Yeah. So maybe the gate itself may have been wood, because that would be slid in. You don't want it to be too heavy when you want to pull it up, right? How am I doing on time? Okay. Now, so what we could gather is that this dam by design is meant to allow flow in both directions. That is why the dual control for the sluices, and that is why the peculiar construction, where at one level the funneling of the flow is in one direction, and at another level it's another direction. Now, before I go to how we think it functioned, we can look at simple engineering, do a simple engineering analysis of the dam. If you look at, say, what is the maximum water pressure that would come on the dam, which has to be resisted by the weight of the dam, then the factors of safety look ridiculous. the overturning factor of safety, the overturning moment is so small compared to the weight that you have a factor of safety of 37. And even if you don't have the abutments, the factor of safety for sliding based on the local soil is of the order of 7. With the abutments, the factor of safety would be even higher. Now, and the way it's constructed, there's no chance of the dam being in tension anywhere, so there's no chance of it breaking or cracking up. Now, one might say that this is hugely over-designed, but if you're planning a structure which is meant to last a few thousand years and be subjected to lots of natural calamities or events like earthquakes, then I don't think this is a large factor of safety. It is probably as large as it needs to be. Okay, so what we gathered then is that the main function of the dam is to act as a sort of a bandh during the monsoon and recharge the groundwater on the Uncool side, and prepare the soil for cultivation. And then on the downstream side, it's not a leaky foundation, but it's a natural spring which feeds into the gorge on the Surajkund side. Okay? And after the monsoon, you close the gates and allow the reservoir to build up, both with the rainwater that you have allowed to go through the dam, through the mid-level sluices, and build up to the top level using the springs that are available at the other side of the dam. Now, I don't want to say upstream and downstream, because now both could be upstream and both could be downstream. So the Surajkund side is where you have springs which allow the reservoir to be built up there. And so the top level sluices and the bottom level sluices are used to feed water back into the cultivated area when you have the dry season. Okay? And our initial conjecture was that for this to function, for you to have a reservoir, then you must have another structure which holds the water between the Uncool Dam and the Surajkund. And we felt that there is a bandh here called the Lakarpur bandh, and so we felt the reservoir is this whole thing, and this is what completes the system. And that's what we conjectured at the end of our first study. And only when we actually looked at we actually surveyed this area, we found that that cannot be true, because the top of the dam is at 230 meters above sea level, and the top of this bandh, the Lakarpur bandh, is only 220 meters. So that cannot hold, you cannot hold the water between these two. Okay? And so the second student I had, Vijay Srinivasan, and I and Professor Oberoi were breaking our heads over this and looking at the contour maps to figure out what was going on. And we were fortunate, we had a non-specialist, my wife, who's a philosopher, and she suggested that maybe there's one more dam that closes the system other than the Lakarpur bandh. And actually, when Vijay looked at the contour maps in detail, he found a candidate position where a second structure could be placed, which allows this to be a coherent system. Okay. So if you, I don't know if these contour maps are clear enough. This is the contour at 230 meters above sea level, which is the top of the Uncool Dam. And if I follow that back, there's another region where it narrows, and we could put another structure here, which could then allow water to be trapped in this region, and the water could then be used for cultivation in this part. The Lakarpur bandh is here, and that is at 220 meters. Okay. Now, as I said, the Uncool side, the land is much flatter. You can see the contours are much wider spaced. Here, the contours are closely spaced, indicating that there's a deep gorge. Now, again, we were fortunate that these contour maps are available and made well before our first visit to the site, because when we visited the site in the mid-90s, by then this spot was destroyed completely, because there's a lot of mining, quarrying activity going on there. A lot of construction in Delhi benefited from the stones that were quarried in this region. So this part was completely, the land was much flatter than what these contour maps indicate. Okay, but these maps were obviously made much well before the coring activity started, and therefore we were able to locate a candidate position for the second structure, what we call the Surajkund Dam. And the field here, if you follow the 230 meter contour and extend it to the 235 meter contour, then we have about 300 to 370 acres, which could be cultivated from the water stored by these structures. So this was the hypothesis that Vijay Srinivasan worked with, that to allow the system to function properly, there must be a second structure, which he called the Surajkund Dam. And of course, you would need some flow control through this device also, so that we can make the entire system function. So not only is there a second structure, there is a gate possibility of controlling the flow in the middle of this structure also. He also investigated the natural springs in that area, and he found that there was one spring here at the base of the dam, which is what led to the conjecture that the foundation is leaking. There is one spring that feeds here, and another spring that feeds the same system here. There are several other springs, one feeding water to the Surajkund temple, and there's another Gurukul here where also there are some springs. But the two springs of interest are what are called SP1 and SP2, which fill up the reservoir that's trapped between the Uncool Dam and the Surajkund Dam. Okay.
So,
yeah.
So like you said, these counter studies used to predict where would be the second gate. Yeah. So, and you said the dam structures were completely destructed when you did the counter study. So, yeah. How was the height concluded? Like, what would be the height of the Surajkund Dam, the other gate, or what was the height of the Lakhanpur Bandh?
Lakhanpur Bandh is existing.
Okay.
The quarrying activity happened between the Anandpur Dam and Lakhanpur Bandh.
Okay.
Okay. So there is no evidence. We don't have any evidence for the Surajkund Dam. This is our hypothesis, okay, that it must have been there for the system to work. Okay. On the other hand, there's no evidence to disprove our theory also. So that's a okay. Yeah, and so you can see that the positioning of this dam is very crucial. It is at a region where the contour is narrow, but it's also positioned in such a way that this spring feeds into the reservoir and not into the Anandpur side. Okay. Then we can go through a bunch of numbers. If you look at the Vijay actually sort of digitized all the contour maps so that you could calculate the area enclosed in each contour and then estimate the volume of water that could be stored on either side of the dam if during the monsoon and so on. And he also, so what he found was that as I said earlier also, the area between the 230 and 235 meter contour and the area enclosed by the 230 meter contour are given here. So the total cultivable area is about 1.7 square kilometers. The volume below the 230 meter contour is about 0.7 million meter cube. The volume in the capacity of the reservoir on the Surajkund side between the Anandpur Dam and the Surajkund Dam is about 1.2 million meter cube. And the catchment area that allowed water to be fed into the system from the surrounding area is about 13 square kilometers. This catchment area was destroyed well before we did our survey. So when we visited the site in '95, there was no large flow coming into the dam area. Now the other numbers that we need is that the local rainfall is such that you have about 0.5 meters of rain every year in this area, and therefore you can calculate that from the catchment you would get about 6 million meter cube. And if you, Vijay was also able to use gauges and estimate the flow coming out from the two springs, And if you add that up, you would get another 6 million meter cube per year. The evaporative, okay, thank you. Oh, the evaporative loss is about 2 million meter cube. So you can see that what is available is about 6 times what is lost from evaporation in the total surface area covered on both sides of the Uncool Dam. One can also look at what is required if one actually goes through cultivating 2 crops, rice and wheat, the Rabi and Kharif crop. And I think we used fairly conservative estimates, and we found that the total volume required for both crops is about 2 million meter cube. So if you discount the evaporative loss, the system in principle can yield about 5 times what is required for the cultivation. So you need only about to successfully trap about 20% of what is available to be able to cultivate both crops. And again, if you then convert it to numbers with this area, how much rice you can cultivate, how much wheat you can cultivate, and what the per capita consumption is, it's very conservative estimate is that it could support about 5,000 people. If you were more stringent, you could one could argue that it can support about 10,000, a population of about 10,000. Okay. And which is not then it's more like a town rather than a village. So it's likely that the produce from here did not just stay within Anandpur village, but also help the Tomar kings supply to parts of Delhi. I will go briefly through this argument. To allow the system to function, it's not just enough to have the water available. One needs to have a fairly fine control on when and to open and close different gates in the Uncool Dam and in the Surajkund Dam. Now, we found that we have 3 choices here, and if we add one more in the Surajkund Dam, then the entire system can function well. Okay. If you want a detailed discussion of the entire sequence of in which month to open what gate and so on, you can look at Vijay's thesis. I'll just briefly go through the argument here. Now, during the monsoon, you might want to partially flood the Anandpur side, but you don't want to trap all the water there because then you can't cultivate anything. So what you would do is keep this gate open and this gate open so that the water would fill up to the ground level on the Anandpur side, and the rest is drained into the Peacock Lake, and it will go through the Lakapur Bund and flow into the Yamuna. So during the monsoon, both these gates are kept open. So the water can accumulate up to the level of the middle sluice in the Anandpur Dam, which is the ground level on the Anandpur side. Okay. You might, towards the end of the monsoon, close this gate, which is gate number 2, and allow the water to build up a little bit so that you can have some flooding for rice cultivation. So the seedlings usually are submerged to allow them to survive pests. Right? So you can close this gate and allow some flooding here so that you can plant the seedlings. And after that, you can transport the seedlings, and then they are quite hardy. Then you don't require the flooding anymore. After the monsoon is over, you close this gate and close this gate also, so that now the reservoir fills up. Okay. Once the reservoir is filled, the excess can flow over the Surajkund Dam, and all that water is available for you. This, as we said, stores about half of what is required, and as it's used up, your underground springs recharge the rest. Okay? So that is how you can get the entire system to function. So this is the main conclusion. The Anandpur the second dam is required to complete the system. And if that is provided, then you can cultivate 2 crops quite easily, and very comfortably you can support a population of 5,000. There are several peculiar features about this dam, that it uses both surface runoff and underground springs to allow it to function, and it's a bidirectional dam. There are a couple of other, the scale is such that it's very easy to maintain, so the siltation problem is not very crucial. There are a couple of other features which prevent siltation. One is that if you look at the Surajkund side, where you have the main reservoir, then the spring is right at the base. So any silt that is likely to settle near the base of the dam is kept in suspension by the spring flowing into that region. The other feature that prevents siltation is the stepped form. Now, there's a very interesting work that shows that if I have a slope, anything that's non-vertical, then the rate at which silt accumulates on that is an order of magnitude higher than what would happen on a vertical or a horizontal surface. And the reason is that when you have a, I don't know whether I can draw it here. When you have sediment depositing here, gravity forces the sediment to slide down the slope, and this creates a secondary flow which sort of brings more sediment down. And this mechanism is absent if you have a structure like this, because it will just sit there. And so the stepped construction, maybe it was designed only for ease of access to different parts of the dam, but it has the great positive side effect that it prevents sediment siltation also. The other thing is that the main structure itself is in such good shape that if the catchment area is restored and the reservoir is restored, it can still function. We are still left with one open question. The temple or the Surajkund pond and temple are within 1.5 kilometers from the Uncool Dam. Is there a relationship between the two structures? We have not been able to figure out an engineering relationship. There may be obvious cultural relationship, that is, when you have something that is as important to your survival as a dam, you might want to create a temple so that people respect it. But beyond that, we have not been able to find something. But I wouldn't be surprised if there's something deeper than that. Okay, what is the situation now? This is a photograph that was taken in 2014. And you can see that now this gorge is completely flattened. The quarrying was supposed to stop, but I think it started illegally. And this area is completely flat now. So there's no question of creating a reservoir here. This part is also being encroached upon. And if you go to a picture that I downloaded yesterday, you can see this is the dam. And you can see that everything is finished. The dam is preserved. It is a protected monument. But it's pointless preserving the dam if you don't preserve the entire system. So it is now really a museum relic. It's not really a preserved structure anymore. Okay. This is a logical place to stop if you want to have a discussion. Because I think I've taken a little longer than I expected. Okay. Yeah.
What time did approximately the dam system stop working? So that Surajkund Dam you mentioned. So is there any?
Yeah, we don't have records, but it at least 200-300 years, because I think there was some surveys done in British time, and then also there was no mention of the dam being really functional. And the later ASI reports don't mention anything other than the dam. And the reports, the interesting thing is that even the earlier surveys don't mention the second structure. Obviously, when we did our survey, we couldn't find even traces of the Surajkund Dam because the quarrying activity had started. But the earlier reports don't mention that, so that is still a conjecture. On the other hand, the earlier reports don't connect the Lakarpur Bandh also with the system. So they looked at it in isolation. Okay. So I really don't know till when it was functioning. Yeah.
So, like you mentioned in the modern scientific methods, when they built a dam, it has adverse effects on the nature and all. But as well, I mean, on the contrary, the traditional dams didn't have it. So, can you please explain how did they have it? Like,
see, one is obviously the scale is much smaller, and this is not a region where I guess the water was flowing through this region. It was a channel that was feeding into the Yamuna. Okay. So you're not creating a flow in a region where it did not exist before. So that is one difference. The other thing is that yes, you will have once you put this structure in, you will be inundating some part of the region, but the way it's designed, it is only inundating enough to cultivate rice. So it is not a major change from what existed before. Water must have been flowing down this entire plain into the gorge and into the Yamuna river, even if before the dam was put there. What you did by putting the dam is allowed locally the water to accumulate a little more, so that you could use it for rice cultivation. But other than that, that entire area was subjected to water anyway. Okay.
so
So that you have not made a major change there. The other thing is also you have designed a system which is easy to maintain, so it can keep going and give you benefits over thousands of years rather than just 100 years or the lifetime of a couple of generations.
So, do the modern scientific methods do not ensure to have a dam in the natural way of water, like you said, if it's flowing in, it's
No, so a large project, when it does the cost-benefit analysis, if you do it really properly, maybe you will not be able to justify anything. Okay, so I don't know. The thing is, when you submerge a forest, how do you estimate what the cost of that is? Is it the timber that you could get from the forest? Is it the fruits? Is it the cost of that is the value of the forest? Or is it the environment cleansing it will do over the next 1,000 years? Is that the cost that you're paying? So how do you judge? It's very, very difficult when you make a large intervention to see what the real cost is, right? So yeah. Okay. It's not the dam in our normal sense. It is sometimes a dam, it's sometimes a bandh. It is a bidirectional. If you want the best description is that it's a bidirectional dam.
It's a bidirectional dam. All right.
Okay. Yes.
All right. Have you ever come across in the ancient literature of civil engineering, of whatever, any such description of a bidirectional structure?
No,
Because I can't remember also.
No.
You've not come across.
No, I've not come across.
That I think
The sources are very limited.
yes.
Apparently, this Samarangana Sutradhara is being translated now.
Huh.
Maybe that might throw some light because there apparently a large number of structures were discussed,
we'll have
but
to
the
check.
translation is not out yet. And I am challenged in Sanskrit. I'm
We'll try
extremely
to check that.
poor there. So.
All right. Then this second dam, which is assumed to have existed, what is it?
Surajkund Dam.
Surajkund Dam. Have there been absolutely no excavations in the area? Because at least the foundations would be there somewhere.
No, that area is flattened now
It has been flattened.
completely. Even when we got there, a lot of it had been quarried already. And what we constructed is only from the old Survey of India maps.
So, but in the British reports which you mentioned,
No,
is there any
no,
reference to that?
no.
So it's purely hypothetical.
Yeah,
as
it's
of now.
purely, as far as this thing. Now, the one thing I mean, if you want to push the argument, it is very likely that the second structure was not a solid structure, because for flood control, you would want that to break and allow the flood waters to discharge easily. So maybe it was a temporary structure and rebuilt periodically. So that could be one reason why no trace of it was left. And if the kingdom goes into ruin, that's the first thing that would be lost. So I mean, I have an answer to that, except one more conjecture. I'm sorry.
Yes.
Yeah.
Yes. Lastly, at present, during a good monsoon, what happens to this?
I think the catchment area has been, all the flows from the catchment have been diverted. So it really, you don't get any flooding.
So there's no chance of
No.
anything happening.
So both sides have been destroyed. Only the dam has been preserved.
And
So-
finally, have you ever heard of any such bidirectional structure anywhere else in India?
No, I'm not aware of it, no.
Of course, many structures have not been properly
Okay.
studied, but
Many structures are not so well preserved as this one is also.
yes.
This one happens to be really well maintained. Yeah. No, so the historical records are unclear.
Okay.
Some records say that King Anangpal, it's clear that one of the Anangpal kings built it.
No,
Whether it's
like-
Anangpal 1 or Anangpal 2, people don't know.
Might be, but my question is, if both of them were successors, how the time period is so long? Like,
No. They're all Tomar kings, and after 300 years, I think the king was called Anangpal again.
sure.
In between, there's a Surajpal who built the Surajkund temple. Okay, so they're all Tomar kings, but they're not Anangpal kings. They're Tomar kings. Okay. Yeah.
Sir, you mentioned the contour plots. So when were they taken and what?
They must have that must have been early 20th century when the large survey of India was done. That must have been the time when they were. It was well before. Fortunately, it was well before the quarrying activity started in that region. So if you have the patience to go through the Rajasthan system in a few minutes, or I could postpone the discussion to tomorrow, as people wish. But people have had enough of. Still have time? Yeah, that will take about 10 minutes. So that's not a major. So, so if there are no more questions, I'll just briefly go through the system. It's a much simpler problem, and so it shouldn't take too long. So this is what is called the kuin-par system of Rajasthan. Kuin is a well. It's not a very deep well, and we first learned about this in a lovely book by Anupam Mishra called the book was written in Hindi. It's called Rajasthan Ki Rajat Boonde, and it loosely translates to the radiant drops of Rajasthan. There's fortunately an English translation available, and that's why I was able to study it in detail. So this is the traditional sort of water harvesting structure or drinking water structure that's found in the arid regions of Rajasthan. The par system, the entire system is called the par system. It consists of a kuin, which is the well, and an agor is a pond surrounding the well, which in the monsoon is full of water. Okay? And the agar is what is the catchment. So this is the local terminology, kuin, agor, and agar. The three together form the par. Okay? So here's the, this is the field work that we did in in 2003, I think, yeah. So this is a typical par system. This is close to Jaisalmer. It's called the Kadera par. Okay. We had gone there after 3 years of continuous drought in Rajasthan, and these wells still had plenty of drinking water. Okay. Now, the depth of these wells is not very high, maybe 5 to 6 meters. But the water table in Rajasthan is more than 100 meters deep. It's about 150 meters deep. Okay. So this is a sort of cartoon about it. What is the way the system works is like this. As I said, the water table in Rajasthan is very low. It's about 150 meters to 200 meters below the sand. And even if you take the trouble to go down that deep and dig a bore well, it is pointless because that water is brackish. It's not potable. Okay. But the locals have found that in several parts of Rajasthan, there are these elevated impervious layers. They are either gypsum or multani mitti, and which could be quite close to the surface, so about between 5 and 10 meters below the surface. And once they discover this region, what they do is they sort of structure the catchment area, so all the rainwater is diverted into the region where there's an elevated impervious layer, and the pond is built around that. So in the monsoon, the entire region is full of water, and there is a bund put around the pond so that the water is stored there. And after the water evaporates, the water is trapped in the wells, in the sand below the pond, and the water is trapped through these wells. Okay. Now, the important thing to note is that if one built the same structure, if you had a rocky region below a clay soil and trapped water there, it would not last more than a season. Okay. It is only because of the special property of sand that the water is retained for, as we discovered, for more than 3 years. Okay. And the basic physics is quite straightforward, and Anupam Mishra ji has a very poetic way of describing it. He says, unlike clay, sand does not form strong bonds. So when it opens up, it collapses back on itself very easily. And it's just like if two acquaintances, they can fall apart without any problem. But if you have two close friends falling apart, then it's a violent separation. Okay? And so clay forms strong bonds, and when it opens, it cracks up very violently, and therefore all the water is lost to evaporation. Okay? So that is the basic physics of this. You find the impervious layer, and then you trap all the catchment, the rainwater from the local catchment into, divert it there, and then you, during the monsoon, it's a pond, and then after the rains, it can provide drinking water, in this case as much as 3 to 4 years. It was still, the tanks, the wells are nowhere close to empty. Of course, the water is only used for drinking. And if you go back, there's one thing. The mouth of the well is quite narrow. It's about 1/10 the area of the actual well, and that's enough for you to sort of access it through with a bucket and rope. And if you look at the thing around this, the well is marked with this stone structure, and around it are these two small sort of containers in which water is poured for animals. So anyone who draws water from the well fills this up also, so that the animals in the surrounding area also have access to water. In spite of all this, the water was available for drinking for more than 3 years. Okay. The other thing, this particular catchment, the catchment area was 16 square kilometers, and the tank area was about 17 acres. And we had, I think, 3 or 4 or about half a dozen of these wells placed at different parts of the tank. We went there in the middle of May, where the ambient temperature was well over 50 degrees. The sand surface temperature was over 50 degrees. But the water was always, whatever time of the day, it was at 24 degrees. It was absolutely fit for drinking, and it was very, very refreshing. So that is why we say that this system uses the special properties of sand, which allow it to be both heat transfer and mass transfer barrier. It does not allow the water to get hot, and it preserves the water under the sand. So the basic physics is just this. What we decided to do is to see, we did some experiments to see how large a layer of sand you would need for this system to be effective. Okay? So that is our contribution beyond what was already discussed and described so beautifully by Anupam Mishra. So what we did was a simple series of experiments with ferrocement tanks, and which could be filled with either clay, soil, or sand to different heights. And we had a central tube from which we could monitor the level of water in the system. And we had also instrumented with thermocouples to see the temperature field and all that. I will not get into great details, but we had 4 tanks, one filled with only sand, that is tank 1, tank 2 only clay, tank 3 had the top 25% sand, with the total depth of 60 centimeters. So the top 25 centimeters means we had about 15 centimeters or 6 inches of sand at the top, and the last one had 50-50, so 30 centimeters of sand and 30 centimeters of clay. So this is all of them were kept underground to sort of simulate the conditions in Rajasthan. Okay. And so this is tank 1. In tank 2, this photo is not very clear, but you can see that I think this is after about a week, cracks start appearing. In the other 3 tanks, there are no cracks. And this is a detailed view. I don't know whether it's clear. There is a small crack visible here. Now, the real important, or the only result worth mentioning, is the water level in the 4 tanks. And this we monitored over 2 weeks, and we could have gone further also. The 3 tanks that had sand at the top, one 100% sand, one with just 15 centimeters, and one with 30 centimeters, the water drops quite sharply initially because the sand allows the top layer to evaporate very quickly. Okay? So the clay is doing much better there. But after about 4 days, the clay dramatically drops, and after about 2 weeks, the clay tank is completely empty, while the sand is still going strong. And this levels off. I think you could take it for a few months, and it would remain the same. So the message is that you just need a small layer of sand at the top, and you can use it as a very effective barrier from evaporation. Okay, so that's the main result. We had a positive side effect, and that is the tanks with the sand did not have any weeds growing. Okay, so and we found out later that in fact, in certain regions of arid regions of Karnataka, in Gulbarga, apparently this is one of the practices that they rice fields or whatever cultivated fields, they put a layer of sand on the top so that the moisture is held at the root level. And so it is an agricultural practice. We found out later, but it definitely makes sense. And of course, the only thing you have to do is when you're plowing the field, be careful and remove the sand first, and then plow the field so that it can be reused. Okay. So that's the small problem that we looked at. So thank you now.